Hello again. If you're hoping for an extensive presentation of all the features of Valispace, I'm sorry to say that's not what's on the menu today. I want to talk a bit about how we believe future products can be developed even better from a concept perspective and how to think about it. And that's why the talk today is all about why modularized product development is the holy grail of agile hardware development. So let's dive a bit into this, and let's start with the first word here, which I'm throwing out big words, agile hardware development, and let's see how we see that a bit, right? So if you're developing one single product, right, like whichever product it might be, you are already dealing with a whole lot of complexity. Like, it doesn't matter which industry we're talking about, we heard about all of them, you always have a lot of interdependencies, and they often look like this. And these interdependencies make it already insanely hard to build a single product. It makes your team trying to organize around them, you're trying to define clear interfaces, but unfortunately, it's not like in software where you can say, well, this product boundary ends here and the other one starts here and I just define it. But physics is unfortunately not that bendable, as we heard from Livingston yesterday. Physics is always going to be there with you, and it means that if you make, I don't know, your battery slightly bigger, it might also create more heat, which will affect other systems around it, no matter how much you decided that it shouldn't even affect the others. What happens now when you have high complexity? It often leads to change paralysis. What do we mean with that? So it basically means that engineers say that once they figured this out, once it's just working, don't touch. Because it's just too hard to understand what the implication of each of these parts is. And what we've seen in the past is that this leads to the typical things that people talk about, and the bigger and older the company, the more talk about it. They talk about design freeze, right? We've established this baseline, nothing changes from here. Stage gate processes, right? Like, you came until here, nobody touched this anymore, now we go forward because we've decided this part is good. Document versioning, releases, right? It's a way of thinking that is basically coming from the fear of doing a change that could destroy the whole system that you've built up so carefully. So what you get is a bit this graph, right? On the one hand, if you look at the development life cycle, and on the other hand, you see the cost of change. It's basically what Ben said on the panel before. It's the 1, 10, 100 rule, right? Like, you're making a decision today in the early stages, takes you 1 time the amount of time. You do a change later in the engineering process, it takes you 10 times the amount of time. If you find something when it's in customers' hands or has been built, it's going to be 100 times the amount of time to change something. And this approach has a lot of problems. We all know about it, right? We know that certain products cost more and take longer than we thought they would. We know that we have problems that we find at the very end that are hard to fix. This can cost lives if you're not doing it the right way. Lots of politics and money involved and all the things that engineers don't even like because they probably would like to focus on the technology. And it goes across all industries. Being a German, being very proud that our airport at least opened at some point. And this means that all of us are struggling with this problem of facing the consequence of trying to hold on to a system where change is very tricky. And the question is there a better way? And I think we've heard it actually a lot of times in these 2 days that there is a better way of approaching it. We heard it in different phrases. We heard fail fast, test as soon as possible, try to eliminate risks in the very get-go. So basically what you're trying to do here is, instead of doing a waterfall approach, you're trying to do fast design iterations. So it basically allows you, by taking on a slightly more higher amount of workload in the beginning, to make sure that you have a system in place that embraces change and that allows you to change something, and in an extreme case, have every product that goes out your door being slightly different, slightly modified, slightly better, learning every time. And I'm very happy, actually, that Bill had yesterday a spiral on his graph. I promise that I didn't steal it from you. It was on my slides before. But here's how we at Valispace think these cycles can and should actually work. So we believe there's 4 parts to quick iteration cycles when it comes to hardware design. One of them is understand. You have to be very, very quick in understanding what the system looks like, what the behaviors are, which ones are the constraints, which ones are the assumptions. So you need to have data at hand that ultimately tells you what your system is. But when I say at hand, I mean it needs to be relevant to you. You have 1 million pieces, and you should be able to look at the ones that are relevant to you. Assess. That means that you're able to make trade-offs, that you say, what would happen if I change this part? Give me an idea. If I make the battery double the size, what does that do to range of my vehicle? It's not super obvious because batteries get heavier. Heavier makes it maybe not go so far, but it changes things on charging cycles, which has to do something with your charging stations and the loading time. All of these other parts are interconnected, and you should be able to assess these things fast. You must be able to coordinate, because engineers, although I have cited multiple times Iron Man who's standing alone in his basement, in reality is a team job. You have multiple people and stakeholders involved, and they all have specific knowledge about it, so you need to be able to get and capture their knowledge quickly. And you need to be able to implement super fast. The moment you have made a trade-off, the moment you have taken a decision that this is what you do instead of that, you should be somehow able to press a button, have the change ripple through, and get to the next problem. If you think of fast design iterations this way, you can now start thinking about how you can, in your organization, optimize each of these 4 parts. If you make each of these 4 parts shorter, each design iteration gets faster. If each design iteration gets faster and have in your company lots of those, not only on the top level, but in every team, then you can have quick amount of changes, learnings, and you can have these spirals, which don't mean that you have to wait a year to be at the same place, but it means you are at a week to be at the same place, or the month to at least, or maybe even a few days to be at the same place, but smarter this time, and can implement the changes. So this is basically how you can approach the idea to go away from a model in which you have to plan all the way until the end to a model in which you are looking into these fast iterations. Now, that means to embrace and to manage change instead of fearing it. It means that changing what you've built becomes the norm, and the better you get at assessing and understanding and collaborating and implementing, the more likely it is that when you find a problem, you can easily fix it and just move on. It's not something unusual, suddenly, in your team to do that. So now we've looked at one product, but now let's look at modularized product development, right? Why modular? Well, when you develop multiple products, it's even harder. All the dependencies that I've just shown are for a single product. The dependencies between multiple products are even higher interdependent. Why? Because you very, very seldomly in a company develop 2 products that have nothing to do with each other. You're always going to build a product that reuses parts of what you have done before. You might have a whole set, an array of products that you're bringing out. You might have a whole family of products that you're bringing out. And all of these are interdependent. And if you're a fast-moving company, you're not waiting for the old version to be retired to build the new one. You're actually bringing out the new one and thinking about the next one while the other one is still going into production. So that means if you want to build products that contain reuse and that allow you to build customizable things for your clients, then you have to think about dependencies. And we believe there's, in principle, two types of reuse dependencies. The first kind of reuse dependency is what we call multi-generation product, or the evolution of a product, right? So you basically have version 1 of your product, and then you have version 2 of that same product, and version 3, and so on. And your product gets better and better over time, right? You make some tweaks every time. You change some stuff. And that's a typical example of what that looks like, right? You have a product, and it's coming out in version 1, 2, 3, 4, 5, 14. And it changes more or less from every version to every version. There is now also a second kind of reuse. And that second kind of reuse is a reuse across different products. So a nice example of this is if I have one battery, and I have 3 trucks, and the same battery goes into 3 trucks. Another example is if I'm building 3 different planes, and in principle they are the same, but one of them is a sports plane with a 2-seater, and the other one actually is a transport plane. They might be built of the same family. So you basically have a product, and it then starts splitting up. Or it might not be even a product, it might be a component or part of a product, like a battery or subsystem or whatever, and splits up. So now you're getting to a whole product line. You're getting to a whole variety of parts. And we see this obviously also in real life already. I think the automotive industry is the most known one, which always had a whole bunch of configuration that was possible, and reusing even across different companies, almost transparent to the customer, because the customer thinks he's buying 3 different cars, and in reality it's all the same one with a different chassis on top. So that kind of reuse exists. Now, where does that get extremely interesting? It gets extremely interesting when you start combining those 2 things that I just talked about. So let's say, take the car example again. You might have 2 different types of cars, right? You might have your sedan car and your SUV, and then these move forward as you improve them, right? You have your version 1, version 2 SUV, version 1, version 2 sedan. Then you have the components, right? You have your different batteries that go into these different cars. So you have the technologies that you're developing, you have parts that you have already used, and it improves and gets better. And then you have features. You have basically properties that are maybe not even a physical component. It might be a mix between software and a mix of thoughts of what it is supposed to be doing. It might be for which kind of elements it's thought for. And now you have all of these, and you want to combine them. And what you actually want to do is you want to do not only combinations, but combinations of combinations, right? So you want to build that new vehicle, and what you do is you say, like, okay, should be an SUV. It should be the battery B, but you know what? Battery B, the latest version, is only going to be ready next year, but I actually need the one that is already ready because the car needs to come out end of this year, so I'm going to use the last version. So it's not always the newest one. It might be even something in the past that you want to use. And I want it to be fully autonomous. And ta-da, you've defined your product of products, which is really, really tricky to now keep track of. So I lied to you when I showed this graph before, because the reality is that's combination of combination is happening here, right? It's not 1, 2, 3, 4, 5, the iPhone, right? There is versions of it, but there's also varieties in it. They may have even different screen sizes, different memories, but they do share some parts which are the same. So you do have that problem of commonality. And this is not only a configuration problem. It's not only a product lifecycle management problem. So in product lifecycle management, for those who are partially familiar with it, you basically say there's a bunch of components, And then you can really well define what went in, for example, which car that you put out, to an extent where you can know at the end, a car with a serial number 123 had this component, had this component, had this component with these serial numbers in it. So even if you get a real call, you can know exactly what went in. That's a great functionality and super important. But actually, you're trying to do systems analysis here. You're trying to understand, before you've built any car, before you have a single serial number, you're trying to understand what the properties of your new modular product are going to be before you've even built it. You want to know what it looks like. You want to know which requirements apply to it. You want to know which tests you have to do. So basically, which data is actually related to each of these elements? Well, there is design parameters, right? So battery A has this property, battery B has this property, battery B star has that property, right? Like, I don't know, a certain amount of milliwatt hours, or things like this. Requirements, right? So maybe you have a sunroof for your car, and the sunroof has certain requirements which say that the car needs to be able to sustain a certain amount of hail without breaking down, and that value might change if you have a sunroof or if you don't have one, right? Or maybe it doesn't. Maybe safety requirements change depending on the configuration that you have. Maybe you have a requirement that comes from a customer which says a sports car shall be really fast, but maybe your van doesn't need to be. Verifications are attached to this, right? You have a certain battery that you have already verified to a certain degree. On a component level, you had it like in your test jig and you did all of these tests, but with battery B star, you haven't done this. With battery C, there's other tests that need to be done because it contains fast loading capabilities, right? You have test procedures that are related to it, a certain amount of tests with certain properties that need to be executed. And you even have trade-offs inside of those, right? Where you can know, well, these are the properties in comparison to those properties. And depending on what you look at, you optimize for one or for the other. So let's come back now to that picture of trying to combine now all of this. So just to make it a bit more complicated, you start now having those same properties, and these properties are attached to each of these versions of each of these variants of each of these either components or entire systems or functions. All of those go into your new product that you just decided you want to build. Or you might want to find out if you should build it, or you might want to find out whether it will provide the right properties for what you're just promising the customer. Can I do that with the old battery? Do I have to wait for the new battery? So what do you get out of this, right? You get out of it the full properties of that new product. If you're doing it right and you're combining that information, you will now be able to know, by running the right calculations and right simulations, what is the full property of this new vehicle? What's the maximum velocity? What's the range? Because it is a mix of all of these decisions that you took, plus some system-level knowledge about how your system is put together. It should be able to tell you how many of your requirements you've actually verified already, right? If I know that I have certain level of requirements that needed to be verified on the equipment level and certain on the system level and so on, you should be immediately knowing, A, which ones are all the requirements that apply to the new thing that I'm building, and B, which ones are all the requirements that of those I have already verified. And that should be able to tell you how many tests there still are to be run, which actually gives you an immediate timeline to how long is it going to take me to bring this thing on the road. You should be able to predict with this how fast you have to go, which things you need to do. And now, as an engineer, once you think of your product in this modular way, you can immediately see how we can come back to the agile part and say, well, if I understand this, I can now assess this, and I can assess whether this is the right combination of properties. And I can immediately switch and take a decision that, oh, this functionality is actually late. what happens if I take it out? You immediately know what happens then with the product, right? And that allows you to collaborate on it and have a discussion on it, which is further away from, I think that our next generation should be double as fast, right? It brings you down to the actual properties, and therefore also to implementation. So what does that enable, right? It enables agile engineering planning, so it allows you to basically come up with a plan that depends on your product. You didn't have to decide which product to build and then think the plan through, but it's the other way around. You know how much each of these small parts will take, and you'll get at least an initial feeling for what your plan now looks like, which dependencies are there, what's the critical path like. You're able to do design optimizations. You're able to say, well, tell me out of all of these configurations, which one is the one that has the longest range, because I have a customer which asking me to build the longest range vehicle I can possibly do. You're going to be able to tell, well, if I want to be optimal on costs or on bringing something to the market right now with all the knowledge I have, which one can I switch immediately? It lets you do project overlapping trade-offs. So now you have 3, 4, 5 project teams, and each of them are interdependent because of the products that you're using in each of them. It goes a bit into the direction what we heard in the last talk. You suddenly have that overview and you know what would happen if. And that's the key question any engineer has, right? On an everyday basis, probably every engineer gets asked 10 times, what would happen if? And answering that question for an entire system, or even multiple systems which are interconnected, works if you think of them as modular parts. So here's my message. Start thinking of your product as a modular product and manage it accordingly. The moment you realize it is modular, then don't start thinking about each version of it as one set of parameters. Start modularizing your parameters. Start being able to recombine them to get to more insights. Because this way you can react faster. If one of these parts doesn't work the way you thought, you can immediately change plans. And that allows you to have fast design iterations, and that means true redesign. So if you're now able to implement changes quickly, you shorten your time to market, right? Because you take those decisions on the way. Even if you get a surprise, you can immediately start reacting. You make less mistakes, right? You don't even go into a direction for too long that is known to be doomed, but you also don't go into a direction which maybe isn't the one that you actually wanted to achieve. And of course, you bring to your customers what they want, which is more customized products, but those on a fast way. Try Valispace. Thank you.
Thank you so much, Marco. Now, before we open up to some questions, just a fairly abstract one from me. So you introduced the concept of modularity, but I've noticed recently that a few big enterprise companies, such as Mercedes-Benz and others, are also talking about modularity. How do we ensure, or how do we know that this doesn't just become another buzzword like digitization or Industry 4.0, and it can actually have dramatic and impactful change to engineering?
I think the key part is to do actually something with it. I mean, it's the same as with digitization. People have actually digitized their companies, right? There are people who have done something, just a very broad word. And that's why I'm trying to put out what we think modular means, right? And trying to be a bit more specific. I think it all comes down to this. It comes down to not just saying, well, modular products in general are good. I think we've been there long ago. Everyone agrees, probably. And everyone who looked at then phones coming out where you can replace parts noticed that you can take it to a certain level, but not to another level, right? So it's not always to think about modular from a perspective of the customer needs to be able to interchange anything. it's more about internal process. And I think the moment that companies look inside and realize, oh, I have all of these parts lying around. Like we work with a customer, for example, who's building machinery, and their machines are highly modular, right? They're really like, basically every customer asks for a machine, they're really, really big, and it's slightly different every time. And they had this idea that they are developing a modular product, but although they knew that, and they know that, well, I can use this or this or this or this, in their internal engineering processes, they didn't set up their work to be like this, right? So they didn't necessarily know the properties that came together because of certain modules, but they just knew the properties of the final product. So I think it's all about changing that mindset and saying, like, if I need to think even in my engineering already about that, and then it stops becoming some abstract concept, but it's more about a way of thinking about your own products that enables you to do more things.
Thank you, Marco, for this very interesting presentation. You're talking about modularity of our products. What about modularity of your own products? For example, do you also offer, for example, only the module of test management? Or, additionally, question, do you offer a module for functional safety, a module for cybersecurity? Are you planning, to which extent are you planning to do this in the future?
Good question. So yeah, Valispace also consists of several modules, and I think software has been developed traditionally always, not traditionally, but for a long time like this, and you know with microservices that you can bring it to an extreme where everything is a module, and then you have a whole array of problems instead of one. So what we find is just because you have a modular product, it doesn't mean that the interactions between them cannot be complex, right? So what we're trying to do is we're trying to think of which modules of our product do exist, but what we're much more interested in is which flows of usage go through that. And it doesn't matter in the end which modules it touches, right? And for us, what we're trying to do is we're trying to solve customer problems of things that they're trying to achieve. So we're talking more and more about those flows. They happen to touch on infrastructure, multiple modules, but the user shouldn't even notice. The user doesn't care whether we decided that this is a module or not. The user wants to, I don't know, create a trade-off between two different things, and whether we call those modules this or this shouldn't matter. Currently, we have therefore the approach to say, we try to help customers to do an end-to-end thing, and they're probably going to find out that we can do other end-to-end things for them. That's why we're offering a software entirely, which allows you to do these things and to even discover which other problems you can solve, instead of trying to constrain our users and telling them, like, you now only have access to this, and you're stuck with this no matter what your problem is. So we're trying to offer basically the capabilities to solve everything in Valispace. And if people tell us, well, but I only use this part and so on, we can always talk about how it's being deployed and how we help your users like understand that flow better. But we don't believe in limiting engineers in their capabilities. We believe that if we're bringing out a tool, it should help them end to end. And if they find out on the way there's more things that it can help them with, they should.
Really good ideas here. I like it. I found it really interesting how you put trade-offs as a property of like individual components. But then again, trade-offs as an activity you can do at the high level. And in my head, a trade-off is like part of the heart of systems engineering. It's the thing you do. So in what format is a trade-off a property?
So what you'll find out if you think about this a bit more is that you're never done with the configuration of configurations, right? So you might actually be able to say something about a whole family of products which has only certain trade-offs in them. I'll give you an example, right? Let's say one of your trade-offs is which color your car is going to be, right? That's a trade-off still to be made if you want to bring them all out or if you just want to bring out red and black next week. Fine. You might still know already that all cars that you're bringing out are going to have this maximum velocity. It doesn't matter anymore which color you pick, right? So you're going to be able to already say things about a certain configuration, even if there's trade-offs to be made inside or not. So the information inside your system, which trade-offs have been made inside and which trades you still can make, that's an interesting one. You're going to be able to bring out boundaries of saying, well, we haven't decided yet whether we're going to go and produce this both for the Japanese and the European market. So steering wheel might still be left or right. But these kind of properties we already know about. No, it doesn't matter whether you're going for this way or for another. So you have the information about trade-offs already in some of these decisions in. And then you can still make that decision later and say, well, for other reasons, for cost reasons, for whatever, I'm still choosing just Japanese market first, which closes the last few uncertainties. But it might tell you already before, the cost is between here and here. And now you go pick and you lower this down for the things that you haven't lowered through, right? And this basically makes the decisions on lower levels already part of how you think of it.
Looks like you were quite comprehensive, Marco.
Around, so thank you very much.